So instead of a phone, I decided to get a brick instead.
Instead of a what?
Instead of a phone, I decided to get a brick instead. And now it's like 3 times heavier.
Oh, that's got power bank behind it. Is it plugged straight into the lightning port?
Yeah. Because my battery is so bad on my phone.
Oh, yeah, okay, that's
like
fair. Is it in S6 or 6S or whatever?
It's old. Yeah. And I already replaced the battery once.
Oh, really?
Yeah. My phone lasts like an hour and a half.
That's what the charger's for, man. Okay, so yesterday we went over basically the last stuff that you actually need to know about for your exam next Tuesday, right? This is the last reminder that you have a poster due tomorrow. This is your second last reminder that you have a major assignment due Monday. Any questions about that? Okay. You have the review booklet and the key to the review booklet are they're on Google Classroom, right? So it's let me know if I can help you out in any way with any of that stuff. But yesterday we were doing half-cell stoichiometry, and was this a particularly easy concept?
Sure.
Maybe. Oh, you never know. Can I just give you a quick practice question? And I'm going to give you 3 minutes to solve it. Is that okay? And I want to see how much you remember. Okay, this is a very typical question. We're asking ourselves what mass of zinc will be plated with a current of 13.5 amps running for 20 minutes. And we could do this in a bunch of different steps, but I've always found that this is it's way easier to solve this problem if you just do it all in one big unit analysis problem. So first thing I want you to be aware of is that this is a stoichiometry problem. The first thing you should do is write down a reaction. Once you've written down a reaction, assign some values to some of your substances, and then go ahead and perform your unit analysis. Let me know if you have any questions about this. I'm going to give you 3 minutes. You probably have about 2 minutes. Yeah, well, you're not going to know. Okay, first of all, what I'm going to do is you probably, have you ever taken this?
No, that's nice.
Okay, so you've never seen this unit, 13.5 amps before, you've never seen that unit before. So go into your data booklet and look at what amps are. It's on page 2. Oh my God. So look for the unit amps. Okay, there should be another unit that you can use instead of amps. The unit is A, right? So look for the letter A on the right hand side of that page. Current. Now, what other units? Instead of amps, C over S. Well, you don't know what the hell a C is. So, do you know what a C is? Does it say in there? It's just just to get. Okay. So you could rewrite instead of amps, you could say C over S.
I think it's a little.
Now you don't know what the hell you're writing, and there's nothing else you can hear about it. Right? I mean, there kind of is. There's usage, right? Let's go over here. Look for something to do with.
Oh yeah, you're right. I grabbed the wrong one.
Yeah, I know. these are all little c's.
Yeah, right now.
Where did I
we got
put
like
it?
exam.
So if you had one more electron in one
How do you cancel the electron?
a coulomb is just a certain amount of charge. Just like a meter. This isn't a meter stick or whatever. Just like a meter is an arbitrary unit. At some point in time, some dude just had to pick. This is a meter. And then once we know that this is a meter, now we can standardize measurements between things. Just like a coulomb is a quantity of charge. And you just picked it because you thought that's the exact quantity of charge. Okay? And so you have coulombs per second, okay? You also have coulombs. Cancel out coulombs. You also have, if you wanted to cancel out seconds, is there anything you can
I'm going to do another one.
minutes? Do you know what I mean? So all we're doing is putting our puzzle pieces together. Just listen up here.
Let me go.
So that number, what is it? 60.
Oh, wait.
I see a lot of people do that. They use the slash bold, right? But that means something over something. This fraction is way nicer. Okay, I'm going to give you 20 seconds to finish up.
No, I know what I know.
No.
Are you watching videos, boss?
How do you
No, I know what I did wrong.
More than mine.
5.5, right?
I got it. We're chilling. I know what you have one.
I forgot to do 2 moles electrons.
Just try and listen up. You're going to be totally lost, but just try your best to listen. Okay, let's try this. Anybody get an answer for me? What? 5.5 grams?
Yeah.
Okay, let's put that in the corner. And let's see. Let's see if Lily is correct. Uh-oh. So let's try this. This is a stoichiometry problem. So what's the first thing you should write down? Your formula. Chemical reaction. We're talking about it's giving you something. It's giving you something and asking you about another thing. What is it? What information is it giving you about? What substance is it kind of talking about when I say 13.5 amps? That's electrons, right? That's electricity. So it's saying you've got a certain number of electrons. So how much zinc will react with that many electrons? That's what the question's really asking you. So if we're plating zinc, what does that mean we're making? Zinc solid. And how do we make zinc solid? What's the only way you know how? Zinc ions plus 2 electrons, right? That's the only way you know how to make zinc solid. So I would put some of this information below the stuff in the equation. The 13.5 amps, that's 13.5 coulombs in 1 second, right? Do we know how many seconds this ran for? 1,200 seconds, right? Why? How do we know it ran for 1,200 seconds? 20 minutes times 60 seconds per minute. Good. Okay, so that's that. We're going to need a special piece of information in addition to this. Don't tell me the number, tell me what that extra piece of information is.
Faraday's constant.
Faraday's constant, right? We're going to need that. Okay, perfect. And we want to know what mass of this thing is. Remember, stoichiometry always involves getting the number of moles of this and turning it into the number of moles of that. So how do I go from moles of this to mass of this? You're going to need the molar mass. At some point in time, you're going to need the molar mass. So we're going to look for the mass measured in grams of solid zinc. And what's the molar mass of zinc? 41 grams per 1 mole of zinc. Perfect. So in every 1 mole of zinc, there's 65.41 grams of zinc. Now we want to know how many moles of zinc we're going to make, and the only way we can get that is by using the molar ratio, right? So there's nothing about moles here except for it's a 1-to-2 ratio. So 1 mole of zinc for every 2 moles of electrons. Moles of zinc cancel out. Well, crap. I don't have moles of electrons anywhere here. Where do I get moles of electrons from? Faraday's constant. 1 mole of electrons is exactly what charge? 9.65 times 10 to the 4 coulombs. So now I've canceled out moles of electrons. Now, if only I knew the charge, the total charge that was being transferred. I don't know the total charge, but I know the amount of charge transferred every second is 13.5 coulombs in every 1 second. And I know that we operated this cell for 1200 seconds. So seconds and seconds cancel out, coulombs and coulombs cancel out, moles and moles, moles and moles, and we're going to be left with grams. And so I'm not going to put this into my illegally downloaded calculator, but I'm just going to go ahead and assume that this works out to be 5.5 grams. Am I correct? Yes, Alicia.
Would you round to 5.5 though? Because I got 5.49 and
There's 2 significant digits. That value of 20 minutes, that's still like 2 significant digits. If I said 20.0 minutes, then I would be telling you that we've got 3 significant digits worth of precision here. Yeah, Max.
I used parentheses on Faraday's constant, and I got a wonky number, so don't use those.
Did you get 55,000?
No, I got 2.05 times 10 to the 11. But then when I took away the parentheses, I got 5.5.
Okay.
Okay.
Either
I think you might be multiplying by this instead of dividing
No,
by
I
this.
hate divide. I know that.
Yeah. No. Okay.
Yeah, we can move past.
Yeah, we will talk about this together here in a second. Is that
Okay, I'll
okay?
just erase it.
Sophia, if you gotta go, you gotta go. Okay, so there were. We went through a lot of stuff. We went through so many things yesterday. That what I would like to do is I would like to give you a sheet of paper that is not an assignment, but I'm going to give you about 25 minutes to work on it, and then we're going to try and answer the questions together, and then we're going to maybe run through some extra material if we have some time. So I want to be very clear, this is not an assignment. It's not from art.
I'm not going to. As soon as you know, we're going to put it up.
Okay. Just let you work? No. I would like to go through this.
Oh, I didn't do the net. Oh yeah,
I got 16 days for that. If it's a spontaneous reaction, it's voltaic. If it's non-spontaneous, it's electrolytic. Okay. I'm gonna go through this, and it's gonna be a little bit annoying.
Is it natural to get 60 days?
386 hours.
Yep.
Yep.
16 days. Oh yeah.
Okay, good.
We did it.
16.1 days. It's actually like 16.09.
Yeah, 16.1 days though. Yeah.
16.1 days.
Yep.
Imagine waiting 16.1 days.
to get 80 grams of hydrogen.
Yeah, imagine waiting that long.
Yeah.
More than 2 weeks to get 80 grams of nitrogen.
Oh,
Then again,
if you're using 5.5 amps, it would. You could cut your time in half by using 11 amps. 18. Yeah. No. You could cut that time in half again by using 22 amps. I know. Okay, let's think about this. I'm not gonna just let you work because I want to go through this and then I want to go through some special topics. So this should take, I don't know, maybe 10 minutes and then we're gonna do notes for 20 minutes and then we're done. Write the half reactions that occur at the cathode and anode. I'm not gonna really explain my reasoning, but suffice to say the nickel 2+ is our strongest oxidizing agent and the chloride ions are the strongest reducing agent. So at the cathode, nickel 2+ liquid is gaining 2 electrons to turn into nickel solid. And the chloride ions at the anode are turning into chlorine gas and they're giving off 2 electrons. So the net reaction, what's the lowest common multiple of electrons? 2, right? So we'll have 2 moles of electrons transferred. Good, no problem. Determine the electrical potential of the cell. What was the electrical potential of the cathode? Negative 0.26 volts. And I'm going to subtract the electrical potential of the anode. Positive 1.36 volts. So I'm going to get 1.62, sorry.
yes, sir.
1.62 negative volts.
Whoa. So cool.
Okay, I want to ask you a question that I was just asked. Is this an electrolytic cell or is it a voltaic cell?
The one that's the second option.
No, wait.
Wait.
Oh, wait, no. First option.
It's voltaic.
It's voltaic?
Is it?
Is it electrolytic?
I don't know, you tell
Well,
me.
because electrolytic, it's like chemical reaction. No, wait. No.
Okay, so
Car battery, wait, what's a car battery? What's a car battery? Voltaic, right?
Electrolytic because it's not spontaneous.
Yeah. Voltaic is a car battery. Goes boom.
voltaic produces a voltage that you can actually use in real life. So that's like a traditional battery. A voltaic cell is a spontaneous reaction. An electrolytic cell uses electricity. So there's two different energy changes going on here, but they're kind of the same, but they're opposite. A voltaic cell uses up chemical energy to produce electrical energy. An electrolytic cell uses up electrical energy to make chemical energy. So one, you're storing it as chemical energy. One, you're unleashing that chemical energy as electrical energy. What? Voltaic cell has a positive voltage. It's spontaneous. Electrolytic cells have a negative voltage. Or a zero voltage. You can have a voltage of 0 and it's still technically considered to be an electrolytic cell. Yeah.
Okay, but like, hear me out.
Yeah.
If you took a voltaic cell which produces voltage and
Yeah.
attached it to an electrolytic cell which uses that voltage to make chemical energy, which the voltaic cell uses to make more electrical energy, and it's just
So it's but it's you're talking about like you're talking about not necessarily a perpetual motion machine.
but like,
So you're talking about the electrolytic cell is being charged by the voltaic cell, but then once the electrolytic cell gets charged, it charges the voltaic cell that just died, right?
When you plug in an extension cord.
Yeah, exactly. So at some point in time, Jordy, the voltaic cell will power the electrolytic cell, but when this voltage drops, the voltage of this voltaic cell is slowly going to drop. Why? Why is the voltage of one cell slowly going to drop?
Because it's producing.
Yeah, but also, what are you using up in a voltaic cell all the time?
You're using chemical.
You're using chemical energy, and you're eventually going to run out of chemical energy. Okay, let me be very clear, Jordy, so shut up for a second. Is your voltage dependent on the concentration of your electrolyte? Is the voltage that you get from a battery, is it dependent on the concentration of the electrolytes in the battery?
Maybe?
no. Like, yes. But no. Yes, it is. Because the more reactions there are, the more electrons that are transferred.
The more concentrated your chemicals are, right? The more vigorous the reaction can be, and the more voltage can be produced. So if you have a very low concentration solution, you will produce a lower voltage than you expect to produce, right? Compared to 1 mole per liter cells. Because how do we define standard cells? What concentration? 1 mole per liter, right? So eventually, Jordy, your question is, you have a voltaic cell, it's charging an electrolytic cell. If you start with 1 mole per liter of your electrolytes, sooner or later, one of those concentrations is going to go down, right? You're using up this concentration. So eventually your voltage is going to drop, and eventually it won't be powerful enough to charge the electrolytic cell. So you're just going to get balanced. If that makes sense. Okay, perfect. This question, really quickly, I'm going to give you the answer. Oh, I'm not going to give you the answer, because we didn't calculate it.
Oh no.
What do you guys get for this?
5.0.
Oh, 5.0 what? 02? 03.
2. Oh, apparently I have 3.
Yeah.
Hey, question mark.
If you want to know more details, let me know. The next one, question number 3 was what? 1.89 times 10 to the 16 days. 16.39. Okay, 1.39 times 10 to the 6 seconds, or
16.1 days.
386 hours,
Or
16 days, or 16.1 days.
no.
Epic.
Right?
Crazy.
Let's use math.
16.
How did you get to days? Can you show it?
Yeah, I totally can. Okay, let's take 1.36 times 10 to the 6 seconds. I'm going to, or no, whatever, I'll just draw it on here. So let's take this answer, 1.36 times 10 to the 6 seconds. Okay, Max, how could you turn this? This is going to be complicated, but I hope people just understand me. I'm going to do this step by step. What's a unit that's like larger than a second?
Minute.
A minute or an hour? What do you want to go to? Do you want to turn it into hours or minutes? Okay, let's turn it into minutes. In every 1 minute, how many seconds are there? 60 seconds. So I've successfully, by dividing by 60, I've successfully converted this into minutes. Now, do you want minutes or do you want something bigger than that? You want days. Okay, let's turn minutes into hours. So in every 1 hour, there's 60 minutes. Minutes and minutes cancel out. So I've successfully converted seconds into hours by dividing by 60 2 times. Okay? Well, if you don't want hours, how many hours are in a day? So there are 24 hours in 1 day. So now hours and hours cancel and you're left with days. And you could totally do millennia. You could do centuries. You could do whatever. Yeah, eons, decades. Doesn't matter. You can't do months. Why can't you do months?
Because months are
Not a standardized unit, right? I don't know, 28 days? Is there 20, sometimes there's 29 days?
Sometimes.
Yeah, in 4 months there's going to be 29 days, right?
How many months have 28 days?
All of them.
The answer is December. The correct answer is December.
Oh, okay. Was that kind of okay?
Yes, sir.
All right, whatever. Hey, take out your notes, please. Yeah, we're going to learn about fuel cells. January 26th. Okay, there's extra practice here. The answers to these practice questions are in the back of the text items. So if you want, feel free. There's extra practice here. But we're going to move on. Okay, this goes back to Jordy's question that I think he was maybe just joking about it, but then we actually talked about it.
I was not. I never joked.
You never joke? Good. We're all business in Chem 30. We're all business. You're not allowed to have fun. Stop having fun. Hey, I'm going to draw a voltaic cell, and I want you to describe a problem with that voltaic cell's operation. So I have a voltaic cell here. It's got a salt bridge. There's an electrode. There's an electrode. It's connected by an external circuit or a wire. So let's say I've got copper and copper 2 plus ions. And let's say I've got zinc. And I've got zinc 2 plus ions. And inside the salt bridge, I've got some sort of conducting solution. Okay? So this voltaic cell will absolutely work. 100% it'll work. But it'll only work for a little bit. Why? Describe for me some problems. If I left this battery running for 5 years in a row, what are some problems that are going to happen, Max?
Eventually, there's not going to be any more copper solid.
Okay, it's not that there's going to be any more copper solid, because which side is the cathode and which side is the anode?
I'm assuming the red side's the cathode.
Okay, no. Why? Did we not have this conversation?
No, we did.
Okay. The right side is not the cathode all the time. This is the strongest oxidizing agent. So we're taking copper 2 plus ions, we're gaining electrons, and we're turning it into copper solid. So what are we using up on the left-hand side? Copper ions. Do you think there's an infinite supply of copper ions here? Eventually, will we run out? Yes. Eventually, we will run out of copper ions, and we will totally plate them all onto the copper metal, basically.
I just have a question.
Yeah.
You said if we left it for 5 years,
Yeah.
the solution is evaporated
We're assuming that there's a cap on here. I know. That's because I didn't think I'd have to say it because, yeah, no, I know. But yes. No, that's a phenomenal question. That's a great question. If you left it for 5 years, would it evaporate? Yes, absolutely, 100%. Yeah. Asking a real question. All right. Okay. That's one problem on the left-hand side. Describe for me another problem on the right-hand side. We're going to run out of zinc what? Solid. What's going to happen to the mass of this solid chunk of metal? It's going to decrease. This solid chunk of metal is going to increase, right? Because we're making a solid and we're using up a solid. So what's going to happen if I leave this for 5 years and nothing evaporates or anything like that? Is this battery eventually going to die?
Yes, sir.
It's going to run out of potential energy. It's going to run out of chemical energy. Because either we're going to run out of copper ions or we're going to run out of zinc metal. Fuel cells don't have that problem. Fuel cells don't have that problem, or at least they skirt around that problem. So, I got a big wall of text. Basically, conventional batteries die because you run out of one of those things. Fuel cells skirt around that because they supply a constant stream of fuel the entire time. Can you imagine if we had a giant supply of copper 2 ions coming through here, and if we kept replacing the zinc metal every single time, would this battery ever die? No, because we'd have a constant supply of copper 2 ions, and we would have a constant supply of zinc metals. That's basically what a fuel cell does. So let's take a look at this. This is a hydrogen fuel cell. On one side, we've got fuel coming in from some sort of a tank that contains a lot of hydrogen. So here we've got hydrogen gas coming in. On the other side, what do we have being supplied on the other side? We've got air coming in, and air contains oxygen, and as long as we have a little bit of water as well, okay, or we can just have oxygen coming in, that's totally fine. But as long as we have a little bit of water present, right, the oxygen can come in. And what's going to happen? You're going to have the hydrogen gas turn into what?
Hydrogen ions.
Hydrogen ions. Then the hydrogen ions, they're free to flow through this electrolyte. And once the hydrogen ions match up with the oxygen gas, then what can we make from hydrogen ions and oxygen gas? Water. So all we need is a constant supply of hydrogen running in, a constant supply of oxygen from the air running in, and this is why, I don't know if you ever heard, like 5 or 10 years ago, there was a huge push to get hydrogen fuel cell powered cars. Because what's the only emission that comes out of a hydrogen fuel cell?
Water vapor.
Water vapor. That's the only emission that comes out of it. Yeah.
How come they didn't do it?
A big problem is getting the efficiency of these hydrogen fuel cells. Also, what do you have to supply? Hydrogen. You can't get that from the air, so you have to drive around with a giant tank of hydrogen strapped to your car. Now, does anybody know what the problem with driving around with a giant tank of hydrogen strapped to your car is, Max?
If you had like a fender bender, that'd be more like a crater maker.
Yeah, that's you're instead of having a car with gasoline, I want to be very clear. Gasoline in its liquid form doesn't explode. But gasoline in its liquid form doesn't explode. What you have to do, in order to ignite gasoline, you need to turn it into a vapor first. And when you have a big giant tank of gasoline, is it in a vapor form or is it in a liquid form? Liquid. So it's not really that dangerous. Your hydrogen either needs to be stored in a tank, which means your car gets turned into a Hindenburg every time you drive on the highway, right? So now instead of 100,000 vehicles with gasoline, you have 100,000 tiny little Hindenburgs driving around the city of Red Deer. So would you agree that's much more dangerous? That's incredibly dangerous. So Coroma, another big problem was they were trying to secure the hydrogen in a state where it couldn't explode if you got rear-ended by my 80-year-old grandmother. So and it's really difficult to do that. It's really difficult to store hydrogen in a non-combustible state, and that's one of the problems. Okay. But what I want to focus on right now is this just like any other electrochemical cell? Do you have an anode and a cathode?
Yes.
At the anode, do you lose electrons or gain electrons? At the anode, you lose electrons. So here on the anode side, we have H2 gas giving off 2 electrons and turning into 2 hydrogen ions. That's what's happening at the anode. Then the hydrogen ions can flow across the electrolyte and meet up with the oxygen. Then, once you have the hydrogen and the oxygen, I don't know, I can't remember if it's on here. No, but there is a half reaction that involves hydrogen and oxygen. So at the it's at the cathode. Yeah, it is. It's about 2/3 of the way up. If you look on your data booklet, it's 2 hydrogen ions plus oxygen gas plus 2 electrons is giving us 2 H2Os. Oh no, that's hydrogen peroxide. Oh no. Anyways, on the cathode side, it's oxygen reacting with 4 hydrogen ions plus 4 electrons to give you 2 water molecules. So basically the hydrogen turns into the electrolyte, and the electrolyte crosses over and reacts at the cathode and combines with the oxygen to turn into water. When are you going to run out of power for this thing?
When you run out of hydrogen.
When you either run out of hydrogen, so as long as you have a constant supply, or when you run out of oxygen or air, right? So, but as long as you have a constant supply of both of those things, then you can get this happening here. That's the power of a fuel cell. You don't constantly have to replace the battery. All you have to do is keep supplying fuel. Okay, Chroma.
So do they kind of use this for like rocket ships?
No, they use something that they need a really, really, really quick source of energy from, so liquid hydrogen and liquid oxygen. Or sometimes they'll use solid rocket boosters, which have a really powerful oxidizing agent in it. And it's that really powerful oxidizing agent reacting with a really powerful reducing agent. That's what creates all of the energy. So it depends on what kind of I'm not a rocket scientist, but those are the 2 main types of engines, yeah.
So how does like a rechargeable battery work?
A rechargeable battery is what are you going to run out first of here? You're either going to run out of copper ions or zinc metal, right? So when you recharge it, you force the reaction to go the other way. So you force the copper metal to turn back into copper ions, and you replenish it. And then you just use the battery over and over and over again. Yeah. Max?
One question. because fuel cells, like, they're really effective and they only run out when they run out of water and air.
Yeah.
Does that
Hydrogen
mean
net.
humans are fuel cells?
No, because, well,
By definition.
okay, in a fuel cell, you need something that is the cathode and the anode. Like when I look at this thing, this is a fuel cell. There's a wire that's attached to a cathode and an anode. And in between is a porous electrolyte. Okay, so you do not have a cathode and an anode in you. No, because each of your cells operates as a tiny little fuel cell, right? The mitochondria is the powerhouse of the cell. So, in your mitochondria, right, you have a series of repeated redox reactions involving. I'm not a biologist, but has anybody taken Bio 30 before? Like NADH and NADPH and NAD plus and stuff like that, or whatever. So technically there is a series of redox reactions there, but whether or not there's electrodes, I don't know. Max, sure, you're a fuel cell. Why not? Whatever. Okay, what I want you to do is I want you to look at this question. Take 2 minutes, look at this question, and there is a diploma exam question, or 2 of them, that I want you to try and answer. So on the left side you got methanol, on the right side you have oxygen and hydrogen ions. Try and answer those questions. Yeah. It's the same as what causes the copper ions to plate onto the electrode? What causes the zinc to turn into the zinc ions? There's a voltage across this wire, across these 2 half cells. There's an electrical force that's forcing the electrons to go from one side to the other. It's